Like I mentioned in the previous video, and just to reiterate, soil forms a triangular distribution of pressure, generally, so non-cohesive soil. And the deeper we go, the greater the vertical pressure from the soil weight above. You can think of this just like water, except the vertical pressure is converted to a horizontal pressure with the K coefficient, which is our coefficient here. Unlike water, which is a liquid, and the horizontal pressure is assumed equal to the vertical pressure. The pressure is the same in all directions. So for this, calculating K, there are two major theories, Rankine and Coulomb. Rankine theory is best used for vertical walls in a flat or uphill backfill slope, while Coulomb theory considers inclined walls, external friction, which is the friction between the soil and the wall surface, unlike internal friction, which is the friction internally between soil particles. So we can consider both uphill and downhill slopes behind the abutments with Coulomb theory as well. I've drawn two diagrams here to show the difference. We have the Coulomb and Rankine. And we'll move forward using Rankine theory because we do have vertical back walls, and the fill is almost always sloping uphill behind the abutments. You can find the equations for Ka, the active earth pressure coefficient, in the EIA Bridge binder, volume 2 for design. So, this is a reiteration of the Ka equation, and you can find this in the EIA Bridge binder, volume 2. So let's take a pause for a moment here, and given an internal angle of friction of 30 degrees and a backfill slope of beta of 10 degrees, using this equation, what would our Ka, our active earth pressure coefficient, be? Correct. Ka would be around 0.35. So make sure you double check that's also what you're getting for your answer, and we can move forward. And we're going to talk about calculating the active resultant. So now that we have our coefficient for translating vertical pressure into horizontal pressure, we can do just that. So let's take an example retaining wall for simplicity. We have a wall of 10 meters in height, and a soil-specific weight or unit weight of 1,800 kilograms per cubic meter. So our horizontal pressure distribution is triangular with the maximum pressure of 61.8 kilonewtons per meter squared. And I get that value by the equation here. And then I'll use 9.81 over 1,000 to convert from kilograms to kilonewtons. So just make sure that's included in your calculation if you're following along. So we now have our area load of our pressure distribution at the bottom of that triangle. All right, so this is our maximum pressure that is forming at the bottom of the wall. And now remember, or also we're going to take this per meter of wall. So we then actually have 61.8 kilonewtons per meter along the wall per foot of wall. And that is this value here. And we can then take it one step further to find the active resultant, which is our capital P, or capital PA. And that's going to act at h over 3, or 1/3, up from the base of the wall. And why is that? That is because, like I mentioned before, it acts at the centroid of the triangle, which in the vertical direction is just 1/3 of its height. So P, the active resultant, is then just the area of the pressure distribution triangle, which is going to be 309 kilonewtons. And you can see the equation here. Our capital P is our lowercase p, our area load, which we convert to a line load because we're just taking this per meter of wall, multiplied by the height of the triangle, h, and then divided by 2 for area of a triangle.